Good day. This is MEG 224 Engineering Mechanics 2 Dynamics. Lecture 9. Planar kinetics of rigid body. The principles of impulse and momentum. Part A. This can be found in chapter 19 of Engineering Mechanics Dynamics by R.C. Hibella. Lecture objective: to develop the formulation for linear and angular momentum of a body. So, linear and angular momentum. The principles of linear and angular impulse and momentum will be used to solve problems involving force, velocity, and time as related to the planar motion of a rigid body. Let's formalize the method for obtaining a body's linear and angular momentum, assuming the body is symmetric with respect to an inertial XY reference plane. Linear momentum. The linear momentum of a rigid body is determined by summing vectorially the linear momenta of all the particles of the body, where L is equal to summation MIVI. Since MIVI is equal to MVG, we can also write L is equal to MVG. This equation states that the body's linear momentum is a vector quantity having a magnitude mvg, which is measured in kilograms meter per second, and a direction defined by vg, the velocity of the body's mass center, angular momentum. Consider the body in figure A, which is subjected to a general plane motion. At the instance shown, the arbitrary point P has a known velocity Vp, and the body has an angular velocity omega. So, therefore, the velocity of ith particle of the body is Vi is equal to Vp plus V of I with respect to P, which is equal to Vp plus omega R, because V is omega cross R. So the angular momentum of this particle about point P is equal to the moment of the particle's linear momentum about P, as shown in figure A. Thus, the angular momentum is R cross MIVI. MIVI is the linear momentum cross the arm. So, expressing VI in terms of Vp and using Cartesian vectors, we have that M is a constant. So we can bring out M because M is commutative. So you can put it anywhere and it will still work. So now is MR cross V, and then VI is VP X plus VPY, that's in the X direction for VP, plus omega in K direction, plus R XI plus YJ. So, and we know that K cross I is J, and K cross J is minus I. Therefore, we have this. So, if we let Mi be is equal to dm, that is the differential mass, and it's creating over the entire mass m of the body, we have Hp is minus integral y dm for this with this, then integral r squared dm in the limit of m omega. This is I, that is the mass moment of inertia of the body about the center of gravity. So here, Hp represents the angular momentum of the body about an axis Z perpendicular to the plane of motion and passes through point P. Since y bar m is integral y dm and x bar m is equal to integral x dm, the integrals for the first and second terms on the right are used to locate the body's center mass with respect to P. So this is the x bar and this is y bar, and G is the center mass or mass center. Also, the last integral represents the body's moment of inertia about the point P. Therefore, HP is this plus IP omega. This equation reduces to a simpler form if P coincides with the mass center of the body. And then in that case, X bar is equal to Y bar, which is equal to 0. Hence, Hg, that is the angular momentum, is Ig omega. Here, the angular momentum of the body about G is equal to the product of the moment of inertia of the body about an axis passing through G and the body's angular velocity. Hg is a vector quantity having a magnitude Ig omega, which is measured in kilogram meters squared per second, and a direction defined by omega, which is always perpendicular to the plane of motion. This equation, this can also be written in terms of the x and y components of the velocity of the body mass center, which is Vgx instead of Vpx, and then Vgy instead of Vpy. Since G is located at coordinates x bar, y bar, then the parallel axis theorem IP is equal to Ig m into x bar square plus y bar square. Substituting into the equation above and rearranging the terms, we have this. So from the kinematic diagram of figure B, Vg can be expressed in terms of Vp, which is Vg is Vp plus omega r, omega cross r. So then their components in x and y direction gives us that. So carrying out the cross product and equating the respective I and j components yield the two scalar equations. Vgx is equal to Vpx, and then Vgy is equal to Vpy plus x bar omega. Substituting these results into the earlier equation yields HP is this. So as shown in figure C, when the angular momentum of the body is computed about P, it is equivalent to the moment of the linear momentum mvg, or its components mvgx and mvgy about P plus the angular momentum ig omega. Using this result, we will now consider three types of motion. One, translation. When a rigid body is subjected to either rectilinear or curvilinear translation, figure A, then omega is equal to 0 and its mass center has velocity of Vg, which is equal to V. So here there's no rotation, it's only translation. So there's no angular velocity. Hence, the linear momentum and the angular momentum about G become L is equal to mvg. And Ag is equal to 0 because there's no angular momentum since there's no angular velocity. If the angular momentum is computed about some other points A, this is A, the moment of the linear momentum L must be found out about the point. Since D is moment arm, as shown in figure A, then HA, that is the angular momentum about A, is the moment arm D times the angular velocity mvg, rotation about a fixed axis. When a rigid body is rotating about a fixed axis, figure B, the linear momentum and the angular momentum about G are, the linear momentum is FVG and the angular momentum is IG omega. So this is omega, this is the linear momentum, and then this is the G is the RG is the distance from the mass center from the point of rotation. So it is sometimes convenient to compute the angular momentum about point O. Notice that L or VG is perpendicular to RG. Then we have that H naught, that is the angular momentum about point O, is the angular momentum of the body about the center, and then this is the momentum times moment hand. So since VG is R omega, here you can replace VG by R omega. So this equation can be written as IG, H naught is equal to IG plus MRG square omega. Using the parallel axis theorem, so H naught is equal to I naught omega, where I naught is IG plus MRG square, general plane motion. When a rigid body is subjected to a general plane motion, figure C, the linear momentum and the angular momentum becomes L is equal to mvg. And then if the angular momentum is computed about A, figure C, it is necessary to include the moment of L and G about this point. In this case, if HA is IG omega plus D mvg, then here D is the moment arm as shown in the figure. Thank you. That's the end of part A. We'll meet in part B. Do not forget to like my video, subscribe to my video, share them, and then press the notification bell for new videos and updated videos. Then if you are one of my university undergraduate students, please do not forget to subscribe with your real name. Thank you. Thank you.